Hello everyone, this is the presentation of the paper, Classifying Historical Cuisines Using Word Embeddings and Machine Learning Models. Welcome, the presentation will follow the following agenda and provide the high-level understanding of our paper. Restaurant menus offer more than just a list of dishes. They provide a window into culinary preferences, cultural values, and historical consumption patterns. These menus not only reflect ingredient availability, but also capture the influence of economic and political trends on food choices. As the sociologist Bourdieu noted, food patterns reveal societal hierarchies and aesthetic trends, shedding light on acquired cultural capital. By analyzing these culinary trends, we can uncover shifts in cuisine dominance across regions and time. While prior studies have explored the link between environmental changes and cuisine evolution, they often focus narrowly on ingredient classification. With ingredient diversity and menus declining, understanding these patterns has become essential for predicting cuisine types and their broader cultural implications. Recent advances in machine learning allow us to approach this challenge with new efficiency, particularly through multi-class classification. Although traditional models using TF-IDF have been common approach, research on word embeddings effect and the application of deep learning architectures for cuisine prediction remain underexplored. This study aims to fill this gap by employing machine learning on multicultural recipe data to predict cuisines from ingredients. By utilizing hyperparameter optimization and comparing the effect of word embedding selection, this research aims to improve model performance in multi-class cuisine prediction tasks. Hence, we pose the following question. To what extent do hyperparameter optimization and word embedding selection improve multi-class classification models for cuisine prediction? To explore this question, we must understand the current literature. The field of cuisine classification combines data science and gastronomy, moving beyond traditional, labor-intensive methods to leverage machine learning. Recent advancements have enabled automated analysis of culinary data, revealing insights into consumption patterns and ingredient cuisine relationships. Early studies used basic models such as naive Bayes, neural networks, and support vector machines with TF-IDF for text vectorization. However, there remains a gap in applying ensemble and deep learning techniques specifically to historical menus. Model selection plays a critical role in balancing complexity and accuracy. Traditional ensemble methods, such as random forests and boosting algorithms like XGBoost and AdaBoost, excel in handling complex data sets and achieving superior generalization. These models are particularly relevant in cuisine prediction due to the diverse nature of recipes. On the other hand, deep learning models like convolutional neural networks, recurrent neural networks, and LSTMs are better suited for sequential data such as recipes, capturing dependencies between ingredients with higher accuracy. Interestingly, while transformers like BERT dominate LP tasks, studies suggest LSTMs may outperform them on smaller, specialized datasets like recipe ingredients. Therefore, for this study, we limited the exploration of deep learning to CNNs, RNNs, and LSTMs. Hyperparameter optimization is crucial for maximizing model performance to enhance accuracy, reduce training time, and improve generalizability. Making the selection of these values a vital part of analysis. Manual searches often limit scalability, while advanced techniques like Bayesian optimization, gradient-based methods, and frameworks like Optuna address these challenges effectively. However, grid search can outperform Bayesian methods on a smaller dataset with a fixed grid space, such as in this study, therefore is picked for this study. Word embeddings are integral to text-based classifiers. Frequency-based embeddings like TF-IDF and count vectorization are widely used in cuisine classification due to their simplicity, while Word2Vec provides richer semantic understanding. Despite their advantages, embedding ensemble methods remain underexplored for recipe-specific context. The reviewed literature highlights the need for further exploration of model optimization techniques and the impact of word embeddings on cuisine classification. Although several models have been applied successfully, more research is needed to determine the optimal combination of hyperparameters, vectorization techniques, and model architectures for accurate and efficient cuisine prediction. This study aims to address these gaps by comparing various classification models and embeddings, focusing on improving accuracy while mitigating issues such as overfitting, precision recall trade-offs, and computational inefficiency. In this study, we systematically analyzed food consumption patterns using restaurant menus. Our methodology focused on three key stages: data handling and pre-processing, classification, and evaluation. First, the data handling process. We worked with three data sets: the NYPL's What's on the Menu, Initiative, Yumli's What's Cooking, Dataset, and Recipe NLG. Together, they provide both historical and modern culinary data. To balance the analysis, we specifically focused on the Waldorf Astoria Hotel menus to address potential biases in overrepresented datasets. Pre-processing involved cleaning the data, encoding features, and text processing to improve classification readiness. For enhanced reliability, we used exact ingredient matching to connect historical menus with modern recipes. Next, the experimental setup and model selection built on prior research by testing a diverse set of models. Traditional classifiers such as multinomial naive Bayes, logistic regression, and support vector machines were compared with ensemble learning methods like random forest and XGBoost. Additionally, deep learning architectures, including convolutional, recurrent, and long short-term memory networks, were applied to handle sequential data effectively. To optimize computational efficiency, neural networks were trained using a predetermined tuning approach with parameters like 64 batch size, 10 epochs, and adaptive moment estimation. Some adjustments were necessary for specific models. For example, logistic regression and SVM, traditionally binary classifiers, were adapted for multi-class tasks by alternating kernel functions. Grid search was used to test linear, polynomial, and radial basis function kernels, ensuring the best fit for the data. Finally, evaluation metrics assessed model performance through accuracy, precision, recall, and F1 scores, with confusion matrices offering deeper insights. Stratified sampling managed class imbalances, impaired t-tests ensured statistical rigor with a significance threshold of 0.05. Notably, instead of relying solely on binary significance indicators, we reported exact p-values for greater transparency. This comprehensive methodology allowed for a detailed analysis of model performance and lay the foundation for improving cuisine classification. For the results, we categorized findings based on the models. Traditional models such as logistic regression, naive Bayes, and ensemble methods like random forest and XGBoost performed reliably with TF-IDF and count vectorizer. In particular, combining TF-IDF with Word2Vec enhanced performance in specific cases. For example, SVM achieved the highest macro accuracy and F1 score with a hybrid approach using Word2Vec and TF-IDF, scoring 0.903 and 0.9011, respectively. This marked a weighted improvement of approximately 19.5% compared to TF-IDF alone. Neural network models showed mixed results. Both RNN and CNN performed better when paired with TF-IDF, while LSTM achieved its highest accuracy with Keras embedding combined with TF-IDF, that is 0.7718. Combining LSTM with Word2Vec yielded slightly lower result of 0.7536, indicating that the choice of embedding can impact deep learning performance. On the menu dataset, TF-IDF embeddings maintained their dominant position, achieving the highest accuracy and F1 scores across models. SVM performed particularly well, with an accuracy of 0.873 and an F1 score of 0.8479. Random forest also showed competitive performance, achieving 0.8621 accuracy and a nearly identical F1 score of 0.8476. Interestingly, random forest paired with Word2Vec surpassed these results, reaching an accuracy of 0.9059 and an F1 score of 0.8972. One observation worth noting is that while the count vectorizer underperformed compared to Word2Vec in most cases and fell short by 8.7% in random forest, however, it outperformed Word2Vec in support vector machine and AdaBoost models, suggesting its continued relevance in specific contexts. Overall, these results underscore the importance of embedding selection and hybrid approaches in boosting model performance for multi-class cuisine classification. The graphs illustrate a comparison of traditional and ensemble models using various word embedding combinations to analyze two datasets: historical menu data, Figure A, and the cuisine dataset, Figure B. The goal is to evaluate model performance and the impact of different word embeddings on multi-class classification tasks. And that leads us to our discussion. As mentioned, this section covers the key findings, their implications, ethical considerations, limitations, and areas for future work. Let's break this down step by step. First, in terms of model performance, the support vector machine, or SVM, achieved the highest accuracy of 0.873 and an F1 score of 0.8479 when using traditional methods like TF-IDF vectorization. Random forest, or RF, performed slightly lower with 0.8621 accuracy and an F1 score of 0.8476. However, when we applied Word2Vec embeddings with RF, we saw a notable performance boost in that the accuracy increased to 0.9059, and the F1 score reached 0.8972. This highlights the effectiveness of Word2Vec for capturing semantic relationships between words, especially when paired with ensemble methods like RF. Interestingly, the count vectorizer outperformed Word2Vec in the SVM and AutoBoost models. This suggests that simpler vectorization techniques can still be highly effective, depending on the model being used. To ensure a transparent comparison, we incorporated both context-free vectorizers like TF-IDF and more dynamic embeddings like Word2Vec. The controlled comparison provided balanced insights into internal and external validity. For example, TF-IDF consistently outperformed other embeddings in terms of accuracy and the balance between recall and precision, aligning with findings from Kilimsi and Al-Shanketi. To adapt the models, ingredients were matched with labeled cuisine classes using a rule-based approach with single character change logic, offering higher efficiency than a probabilistic matching for large datasets. One ethical concern was the assumption that recipes remain constant over time, potentially leading to biased results and impacting external validity. A diverse multilingual dataset was used to mitigate this effect. Another concern was the focus on hotel menus, which may reflect wealthier individuals' dining habits, introducing temporal bias. However, these menus provide valuable insights into both touristic and local dining experiences, useful for studying broader culinary trends. Lastly, reproducibility is limited for algorithms sensitive to random initialization and data conditions. Future studies should maintain consistent pre-processing for replication. Despite these challenges, the study offers a thorough analysis of model performance across datasets and techniques. Future research should consider advanced embeddings such as BERT or GPT, further explore the effectiveness of hybrid approaches, and expand to more diverse historical menus. Additionally, investigating hierarchical methods could deepen the understanding of food classification. As a conclusion, or to give a high-level summary of the findings, no statistically significant performance boost or decrease was observed the applications of mere embeddings. Difference performances across datasets were observed, however, the variances were not statistically significant. TF-IDF excelled with traditional models. Combining Word2Vec plus TF-IDF improved accuracy, 0.903, and F1, 0.9011, with ensemble models. Hybrid approaches for ensemble embeddings outperform deep learning models. Future work should include advanced embeddings such as BERT and GPT, hierarchical methods for food classification, and diverse historical menus to reduce bias. Thank you for listening to this presentation. We encourage readers and listeners to contact the authors for additional information and access to the appendix. Thank you once again, and we hope you have a great day.